Hi, in this video, I will talk about electric potential and electric potential energy. So we will go over electric potential of point charges then, and also equipotential surfaces. And then we will move to capacitors and dielectrics. So let's get started. The two concepts, potential and potential energy, are two distinct but related concepts. So these are related, but they're actually different. So one of them is potential and the other is potential energy. The figure below is about gravitational potential and gravitational potential energy. So as you can see here, so let's say this is our coordinate system. This point is 0, this height is h, and this height is 5h. Now we can write potential energy. I think you are familiar with gravitational potential energy. It's basically mg times the coordinate. In this case, this point is 5h, so mg 5h. At this point, the potential energy is mgh, and at this point, it's 0 with respect to this coordinate system. And if you remove the mass from the potential energy, what you get is potential. So this is potential energy, U is potential energy, and V here is just potential. So just remove M, so what's left is a G, so 5GH, it gives it potential. And in this case here, it's GH, and here it's 0. So this point, the top point is higher potential place, and lower points are lower potential places. So we can make a couple observations. The first one is potential energy depends on the mass of the ball, but potential does not. As you can see, that potential energy depends on mass, but potential doesn't depend on mass. The second observation we can make is that multiplying the potential with mass gives the potential energy, where we can write this formula. So if you know the potential multiplied by mass, it gives you the potential energy. And indeed, it's the case here. If you multiply V by M, so you will get mg5h, so it gives you potential energy. So basically just multiply potential by mass, it gives you the potential energy. So the conclusion that we can make here is that potential is a property of the location. As you can see, that potential, it depends on the position. It doesn't depend on mass. And potential can be defined even in the absence of the ball. So even if there's no mass, we can still talk about the potential of these points. But potential energy is the energy of the ball of mass m placed in that location. So potential energy depends on mass. So think of this way, there is potential at all points, and potential energy is the energy of the mass m, in this case the ball, when placed at any height. So when there's a potential at certain place, and when you place an object with mass m, so then you can talk about potential energy of that object in the background of this potential. So of course in this chapter we will not deal with gravitational potential or gravitational potential energy, but this is a starting point. So we will go with analogies, and we will talk about electric potential energy and electric potential in the next slide. Okay, so here we are interested in not gravity, but electric potential and electric potential energy. So shortly going forward, instead of electric potential, I will just call it potential, and instead of electric potential energy, I will just call it potential energy. So let's start with the battery. So you are familiar with that the batteries, they come with their potential comes in terms of volts. So when you read 9 volts for this battery, for example, on it, it actually refers to the potential difference, not potential energy, but potential difference between these two terminals. So the battery in the figure has potential of 9 volts between the two terminals, or you can say potential difference. So between these two terminals, there's a potential difference of 9 volts. If we connect the terminals with a wire, so let's say we connect these two terminals with wires, so you can have, if you want, you can have some lead here or some resistor, that doesn't matter. So if you do that, then charges will fall or flow from from plus terminal to minus terminal. So just like the ball, remember the ball, if you leave the ball in the previous slide, if you release the ball here, it will naturally go down from the high potential, to a place low potential. So it will naturally move from higher potential to lower potential. The same thing with the charges in electric potential. So they would, because this is low potential or lower potential, and this point has higher potential, so the charges would naturally flow from high potential to low potential. Indeed, that's what gets us the electric current. So a charge at the positive terminal has more potential energy. Remember, there's a higher potential here, and if the charge is here, it has more potential energy. And at the terminal, at the minus terminal, it has less potential energy. So it goes from higher potential place to lower potential place by decreasing its potential energy. So by analogy with, so we wrote this in the previous slide, so we can make the analogy, but now instead of mass, we have electric charge. And in this case, it's the charge of the electrons in the wire in this example. So potential energy is, as you know, the energy is in units of joules. And the potential itself is in units of volts. So volts, if you look at here, so this is in joules, if you do so, and this is in coulomb. So volts is also joules divided by coulomb. So the same thing, instead of joules divided by coulomb, calling it volts, it's an easier or shortcut. So let's look at this example. How would the potential energy of the charge Q equals 3 times 10 to the negative 5th coulomb change if it's carried on a wire from the positive terminal to the negative terminal of a 9 volts battery? We will use this equation, but with delta, because we are now talking about the change in potential energy. So change in potential energy will be Q times change in potential between the terminals. So as this much charge goes from the positive to negative, so that's our Q. And between the terminals for this battery, there's 9 volts of potential difference. So you multiply it by 9. So this will be 9. And when you do the multiplication, you find the energy change of that charge, of this much charge, will be this many joules. Okay, so in this example, what we have is we have a 12 volts battery, connected to these conductors. So these conductors, they're two plates, conductor plates. Conductor means they can you can charge this so it's basically a capacitor. And the two terminals of the battery, 12 volts, they are connected to each of these plates. Now the first part of the question is find the potential created by 12 volts battery at points A and B. So we connect the battery like this, and you will have positive charges here and negative charges here. Now, what is the potential close to or at this top plate? And also, what is the potential at this point? So these are points A and B. And the second part of the question is find potential energy of a charge. Notice that when we talk about potential V, we don't talk about charge. It's about the place. It's a property of the place. But when we talk about potential energy, now we have to place a charge in that place. When you place a charge in the background of potential, then we can talk about potential energy. So charge is given. So part B is what is the potential energy at this point and when the charge is at this point. Now for the first part, take the potential at the top plate, 12 volts, and the potential at the lower plate is 0 volts. So the difference is 12. This is actually delta V. So the difference between potential difference between these two terminals. So we can take this plate at potential 12 volts and this plate at 0 volts. But we could also take, for example, 20 volts and 8 volts. That also works. In fact, there are infinite number of choices. So what matters is the difference between these two numbers should be 12. You can even take this to be 0 and the bottom one to be negative 12. So as long as the difference is 12, then that's fine. It doesn't matter which particular values of potential you choose for each plate. Okay, so we found potentials at A and B. So, and in part B, now we have to find the potential energy. So potential energy at A, so you place a charge at point A. Now we use this equation that we learned in the previous slide. So now we know the potential here, it's 12 volts. And the charge is given in the problem here. So you plug in the charge here, you do the multiplication. So multiply by 12 volts, and this is the energy in joules of this charge, of the object with this much charge, when it's placed at this point, point A. What happens next? What happens if you place the charge at B, at point B? Now you will use again the same formula. It's charge times the potential here. The potential here is 0. Okay. Now you probably notice that the potential energy also depends on the potential, and as you know, we chose these two values arbitrarily. So as long as the difference is 12, then you can choose any numbers. So that means the potential energy at these points, it also depends on your choice. So there is some arbitrariness in these values. But what's not arbitrary, or let's say the thing that doesn't depend on your choice, is the potential energy difference. So choose any numbers as long as they are 12 volts in difference. The difference is 12 volts. Then these numbers, this number and this number, the potential energies at point A and B will be different, but their difference, so UA minus UB, will be always this number for the values given in this problem. And in fact, this is the potential energy difference, or potential difference in this case, 12 volts, is what's relevant experimentally or physically. When you measure something, you don't actually measure the potential or potential energy at any point. You always measure the difference in potential or potential energy. Okay, so we talked about this. So here, positive terminal and negative terminal. Positive terminal is at a higher voltage. So if this is a 9 volts battery, then you can assign to positive terminal 9 volts and to negative terminal 0 volts, but that's not the only choice. You can also do plus 4.5 for the top terminal, and for the negative terminal, negative 4.5. That's also possible because the difference is still 9 volts. Or you can even do negative 8 for the top terminal and negative 20. And as you can see, the difference is, in fact, this is not correct. So if you choose this to be negative 8, so this should be negative 17. So now the difference is still 9 volts. So the point here is the potential at any point, there is some arbitrariness in it, but the difference, what matters is the difference. This 9 volt is the property of the battery, so it doesn't change. But to be able to solve problems, you have to choose one of these, and it doesn't matter which one you choose. The experimentally, or let's say the observable values, like let's say you measure something with the voltmeter, they will be always not the potentials, but the potential differences. So there's an arbitrariness in the value of potential and potential energy for a given point, just like the gravitational potential energy depends on the arbitrarily chosen coordinate system. What is not arbitrary is the difference in potential, as I mentioned, and potential energy difference. So in all possibilities listed above here, we have the potential difference 9 volts. So in the previous problem, we could take potential at A as 6 volts. So we could take this point 6 volts, and at B, negative 6 volts, or any other set of values that satisfy the potential difference to be 12 volts. So the energies, potential energies at A and B will be different, but the difference in potential energy will still be the same. So it will be the same number. So what's important and experimentally relevant is the differences in potential and potential energy, not potential and potential energy themselves. And indeed, voltmeters, they measure potential difference. So when you use the voltmeter and when you measure, let's say you connect these to the terminals of the battery, what you measure is 12 volts. In fact, that's the difference, that's the delta V, the potential difference between the terminals of the battery. So with the voltmeter, you don't measure potential at a point, but you measure potential difference between these two probes. Okay, what is the reason that we cannot measure potential at a point? As we discussed here in the slide or in the previous problem, the potential itself is at a point, there is an arbitrariness. So it's not a definite value. That's why we cannot measure, it's not an observable, it's not experimentally relevant. But what's relevant experimentally, what's the thing that we can measure? It's the potential difference. So existence of a potential difference between 2 points with separation delta x. Let's say we have 2 points and they have at different potentials, let's say 10 volts, 5 volts, and they're separated by delta x. Now, if you have a potential difference like this, we don't have charges, by the way, it's just different points in space. They're just separated and there's a potential difference. Then this creates electric field from high potential to low potential. And the value of this magnitude of this, the value of electric field is given by negative the change in potential. So in this case, it would be 5 volts divided by, let's say, if this is 2 meters, divided by 2. So 5 volts divided by 2 meters, it would give us the electric field produced between these two potentials. Again, these are just 2 points, not charges. Of course, there are some charges at different positions that create these potentials, but we are not here interested in charges, but we are interested in the change in potential with respect to the space. The SI unit of electric field can be volts per meter, as we saw here, or as we learned in chapter 19, it could also be Newton divided by Coulomb. So these two are equivalent. Now here's an example. Calculate the magnitude of the electric field between the plates connected to a 12-volt battery. Now there is a potential difference here, right? So the potential difference between these two plates, now because they're connected to different terminals of the battery, the potential difference is 12 because here we have a 12 volts battery. By the way, there's no current between these plates. They are not connected. These lines, they just show electric fields. Now, why do we have electric field? As we mentioned here, if you have a potential difference between 2 points, and there's a distance between those points, as usual, then there is an electric field from high potential in the direction of from high potential to low potential. In this case, the potential difference is 12. So this is 12. And there's a distance of 0.0075 meters. So this is this one. And if you do the division, you will find it's 1600 volts per meter. Or you can also say newtons per coulomb. Same thing. So the bottom line here is if you have potential difference delta V, then you can divide it by delta X, and it will give you the electric field between those 2 points. So again, let's take a look at it here. Now we have a battery of 40 volts. It's connected to 2 conductors. And so let's choose this conductor, this one on the left, to be at 40 volts and the one on the right at 0 volts. Again, it doesn't have to be like this. We could take it, for example, we could, for example, have 60 and 20. So what matters is the difference should be 40 volts. So these values are not, there's something that we choose to make calculations. So let's go with 40 and 0. So the potential energy as you move to the right, it decreases. So it starts from 40 and it becomes 0 on this conductor. Now let's calculate electric field between 40 volts and 30 volts. So here it's 30 volts. Here it's 40 volts. Now there is a potential difference, so delta V, and there's a distance which is 1 centimeter. So the potential difference is 40 minus 30. The distance is 1 centimeter. And if you do the division, you will find the electric field here at these points. The electric field strength is 10 volts per centimeters. You can convert centimeters to meters if you want, or you can just leave it like this. And let's calculate now the electric field between 30 volts and 20 volts. So this point and this point. What is the electric field strength between these 2 points? Again, there's delta V, which is 10 volts. 10 volts divided by the distance, 1 centimeter. We are using this formula. And again, you find 10 volts per centimeters. Now, let's make a couple of observations from here. First, potential V is decreasing linearly between the parallel plates. If you have a different setup, not parallel plates, but maybe curved plates, it could be different. But for parallel plates, the potential is decreasing linearly from 40, 30, 20, 10, and 0. The other thing is electric field is from plus to negative plate, so positively charged plate to negatively charged plate. And that makes sense. That's in line with what we learned in chapter 19. We learned that electric field lines go out from the positive charges. They go out and they go into the negative charges. Here, the electric field is constant between the parallel plates, and as you can see, its magnitude doesn't change. And the density of the electric field lines is not changing because electric field is constant from left plate to right plate. Now, look at the density of the electric field lines. Look at the density here and look at the density here. The density doesn't change. So from here, we can say that the electric field lines, their density doesn't change, so the electric field is constant. Now, what happens if charges move in electric field? How would their energy change? Their potential energy, how would it change? Well, from physics 1, we learned that the change in potential energy is the negative of work. And work is the dot product of force and displacement. So force in chapter 19, we learned that if you have electric field and if you place a charge in that electric field, the electric force becomes Q times E. And we still have the dot product here. Now, if you expand the dot product, what you can do, so let's keep the negative and Q here. So it will be E x component of electric field times x component of displacement and y components and z components multiplied. So these are now scalars, so these are just numbers, not vectors. These are just components. And here Q and these components of electric field and the components of displacement, they can be positive or negative, depending on their direction. So let's look at this example here. So we have electric field in the x direction, and its magnitude is 7 newtons per coulomb. And there's no electric field in the y or z directions, so it's purely in x direction. So for this question, so because there's no y component and no z component, so the change in potential energy will be only this part, which is here. Now, let's analyze these 4 situations. First, let's move the plus charge, this red one, leftward for 3 meters. So we will move this to here, and this is 3 meters. So the charge is +1, and the displacement, sorry, we will move it rightward. So we will move it here. And this displacement is 3 meters. So dx is plus 3. And so now apply this formula. So plug in the numbers. Q, so there's this negative charge from the formula, and there's Q is plus 1. Electric field strength is 7. So we got 7 here. And the displacement, it's in the positive direction. So displacement, we move it this way. This is positive direction. So let's put the coordinate system like this. So right direction is the positive direction. So displacement is plus 3 meters. And if you multiply these numbers, you will find the change in potential energy is negative 21 joules. So the potential energy decreased. Okay. So, okay, we actually skipped this. Let's do this. So if you move it leftward, now move it this way for 3 meters. Now, again, charge is 1. Now, displacement is negative 3 because you are moving it leftward, and we chose left to be negative direction. And plug in the numbers here, and you will find the change in potential energy to be 21 joules. Okay, let's move to the third one. So if you move this charge now downward for 2 meters, so you move it this way for 2 meters. Now charge is again plus 1. Now displacement in y direction is negative 2. Displacement in x direction is 0. So what we have here is E x component of electric field is 7, but there's no displacement in the x direction. So we got 0 here. For the second part, there is displacement in the y direction, but the electric field doesn't have any y component here. So that is 0. So EY is 0. And you can see that this will give you 0 joules. So that what it means is if you move the charges in the perpendicular direction to the electric field, then the potential energy will not change. Now let's move to the negative charge. Let's move it rightward for 4 meters. So we move it here. This is 4 meters. So dx is positive 4 meters. Here, charge is now negative 2 coulomb, negative 2. And if you do the multiplication, now you will find 58 joules. So this is the potential energy difference if you move the charge from here to here. Okay, let's now solve an example where we can use potential, the conservation of energy. So in this example, we have a charged particle, and it's released from point A at rest. So its initial speed is 0. Find the speed VB. So VB is basically, so this particle, it's a positively charged. So there's electric field created by these parallel plates, and also they produce potentials. So the particle will move from the positive to negative side. And in this problem, we ignore gravity. So the particle will move under the effect of electric field or electric force, or if you want, electric potential. Now the question is, what is the final speed? So it started with 0 speed, and what is the speed that it gains when it reaches to this point B? So we will solve for VB. So now we will use energies, not forces. Let's do that first. So we had found the potential energies at point A and B to be 75 times 10 to the negative 6 joules, potential energy at this point, and potential energy at point B, we found it to be 0. Now let's use energy conservation. So initial energy should be equal to final energy. because in this system there's really no non-conservative forces like friction or air resistance. So the initial energy will be kinetic plus potential, but it started at rest, so there's no kinetic energy initially, so it's 0. The potential energy at the top is this value, so we write it here. Now, we equate it to the final case. In the final case, the charge, it will have kinetic energy, so 1/2, this is the mass, which is given here, times v squared. And this is something that we don't know. We will solve for it. And at the bottom, the potential energy is 0. That's what we found before. And if you solve this equation for VB, it turns out that it will gain its potential energy, its speed at point B will be 3.4 meter per second. So you may ask the question, well, these values, there was some arbitrariness in these values, and they depended on the potential that we chose on the plates. That's true, but even if you choose different potential values and find different potential energies at point A and B, as you can see from this equation, what matters is now on the left-hand side we have UA, and on the right-hand side we have UB. These individual values may change depending on how you choose the potentials, but you can see here in this equation, for example, we can send UB to the other side. So on the left-hand side, we have UA minus UB, and that's actually delta U. So delta U never changes. So whatever potential you choose, as long as the difference is 12, and after that, whatever potential energies you find at point A and B, the final answer for the velocity or for the speed will be always this. So there's also an alternative solution where you don't have to use energy, conservation of energy, but you can use electric force. So F equals Q times E on the particle. Find then, by using this force, find the acceleration by using Newton's second law of motion. So F equals ma. So, and once you know the acceleration, then you use kinematics equation. So that acceleration, it comes in here, and you know the distance between the plates. So the initial speed in this case is 0. So from here, by using the forces and the kinematics equation, you can also solve this question to find the final speed. So previously we had parallel plates connected to a potential source, which is battery in this case, and we were able to calculate potential energy from U equals Q times V if the charge Q and potential V were given. So potential is given, for example, here, or the potential difference, and if you are also given the charge, then you can calculate the energy U by multiplying those two. But what if there's no battery, but two charges, Q1 and Q2, and we don't know the potential V? So how can we calculate the energy of these two charges? Now the formula is this one. So you have two charges, Q1 and Q2, and they're separated by distance R. Now what is the energy of the system? It will be K, it's the Coulomb constant, charge 1, charge 2 divided by R. It looks like the force, the Coulomb force, except in the force we have R squared, but for the energy, potential energy, we have just R, not R squared. So this is the potential energy of 2 point charges. Now, what is the meaning of this potential energy? Here, U is the energy that you have to spend to bring two repelling plus charges. So if you have two plus charges, they would normally repel each other. So they wouldn't stay like this. They would repel each other, right? So, or if you have two negative charges, they would also repel each other. So now imagine that you have two plus charges at infinity. They're separated charges and they're separated by infinite distance. Now, suppose that you bring both of them from infinity. So let's say one of them is at negative infinity. So you bring it from negative infinity, and the other one, you bring it from positive infinity. So when the separation is infinite, then the potential energy is zero. And finally, you bring them close, and their distance is between them is r. Now, this potential energy. The meaning of this is the energy that you have to spend to bring these two charges from infinity to distance or to separation of r. So that's the meaning of this potential energy. So it's the energy that you have to spend to bring those charges to close to each other. So if you just release them, of course, they will repel each other and they will go to positive infinity and negative infinity. So, or if you have one negative charge and one positive charge, now you don't have to bring them right together. They will naturally actually attract, they will be attracted to each other. So they will come together naturally, even if you have a plus charge at plus infinity and negative charge at negative infinity, they will attract each other and they will come together naturally. Now, when they approach and come to separation of r, let's say they came and their separation became r, then they give off energy u. Now, in this case, in the same charge case, we would give them energy to make them close, but in this case, they will get closer naturally, so they will give out energy. Or if you don't use that energy, then it will be converted, so you can use that energy, or if you don't, it will be converted to their kinetic energy. So then they would have some speeds. So that's the meaning of this potential energy of 2-point charges. Now, here's an example. Find the electric potential energy. So U for 2 plus 3 coulomb charges separated by 2 meters. So we have 3 coulomb charge here and another 3 coulomb charge here. They're both positive and they're separated by distance 2 meters. And by the way, this energy will be also, it's the energy required to bring these 2 plus 3 coulomb charges from infinity to 2 meters proximity. How do you do this? You use the Coulomb's constant, and the charges are 3 both, and the distance between them is 2. Notice that we don't take the square of it. This is not force, this is potential energy. And the answer is 4 times 10 to the 10th joules. So now for conservative forces, there's a potential energy U associated with the conservative force. So if you have a conservative force F, then there's always a potential energy associated with it. For example, if you have a spring force, which is a conservative force, so you can, for example, you can have a spring, you can compress it, and then later you can take that energy back. So you can release it, and that energy will be released. So it's a conservative force, this is the spring force, and you have the spring potential energy as 1/2 kx squared. Here K is not, of course, the Coulomb's constant, it's the spring constant, and it depends on the spring. Now for gravitational force, the force between two objects, two massive objects, separated by r, and g is the Newton's gravitational constant. This is the force, and you have the gravitational potential energy. It just looks like the force, except instead of r squared in the denominator, the potential energy has just r. Now, we have electrostatic force. Now, the Coulomb's constant, the charges, and divided by r squared, the separation between them, it will give you the force. And associated with that force, there is electric potential energy. And for point-like particles, if you have one particle here, the other here, and the charges are Q1, Q2, and this is the potential energy that we actually learned in the slide and in the previous slide. So again, the difference between the force and the potential energy is basically in the denominator. As you can see, one of them is r squared, the other is r. So another useful energy unit is electron volt, especially in chemistry. Instead of joules, you use electron volts more than joules. So it can be used instead of joules. So now think about this formula that we learned. So E here is the fundamental electric charge. If you remember from chapter 19, it was 1.6 10 to the negative 19 coulombs. This is the charge of an electron or charge of a proton, and multiplied by the potential. In this case, take 1 volt. So it would give you 1.6 10 to the negative 19 joules. So instead of using this small value in joules, you can call it 1 electron volts. So that's just a useful conversion. And ionization energy of hydrogen it's this much joules. So if you convert it to electron volts, it's 13.6 electron volts. Hydrogen atom is 1 proton and 1 electron, as you can see here. This is the energy, the ionization energy, which is here. Or if you want in joules, it's here. This is the energy to separate the electron from the proton. So if you want to break this electron off of this hydrogen, of this proton, so there's an attraction between them. If you break it off, then the energy that you need to provide is this much. If you provide this much energy to this system, to the hydrogen, then you can take apart its electron. Okay, so now let's talk about the electric potential of point charges. We learned electric potential energy, or we just call it potential energy shortly, for 2-point charges. We learned it was this formula. So if you use this formula that we also learned, potential energy equals charge times potential. So basically, let's say you have a region, and in that region you have some potential V. So you don't, even if you don't place any charges here, you can still have potential V created by some maybe plates or other charges around. So now if you place a charge Q1 within this background potential, let's say you place Q1, now the energy of this charge in the background of this potential in this space becomes Q1 times V. So this equation gives you the potential energy. Now, if you compare these two, so if you just separate Q1 here, so if you look at it here, so this term is actually potential because U is Q1 times potential, then this term K Q2 divided by R here is the potential. So this is the first time now we write down the potential of a point charge. Before we talked about the potential of different points of the plates. They were connected to a battery. But now we are starting to talk about the potential that's created by point charges. Here, the potential is not created by Q1. It's placed in the potential. And this V, it's created by some other charge, Q2. So maybe there's this charge Q2 here, and this distance is R. So this Q2 creates potential at this point. And when you place Q1, the energy becomes Q1 times the potential, which is created by Q2. So we can calculate the energy of the system either by using this and this, or by just using this formula, which we did in the previous slides. But the new thing that we learn here is that we can write the potential of a point charge. The potential created by the point charge, Q2, is K Q2 divided by R. And if you want to make a comparison between potential, energy, and potential, difference is both have R in the denominator, but potential has only Q2, but potential energy has both charges. So here Q2 produces potential V at distance R. Again, this is Q2. It produces potential at this point. So this distance is R. And if you place another charge Q1, let's place Q1 here. Now you don't have to know about Q2 anymore, because once you know the potential at this point, yes, it's produced by Q2, but as long as you know potential, now you don't have to know about Q2. Once you have the potential and the charge placed in that potential, by using this formula, you can find the energy of this particle. Now, this table of formulas summarizes all the formulas that we learned so far. We learned electric field and force, these two formulas, in chapter 19. And if you want to go from electric field to force, you basically multiply electric field by another charge. So if you multiply both sides, you can see that Q times E gives you force. So this is force, as you can see here. And the right-hand side will be exactly, it will give you the force. So to go in this direction, you multiply the quantity here by another charge. So in this slide, we also learned potential created by point charge. So it's K Q1 divided by R. You can go from potential to electric field by dividing by R. So if you compare these, so the only difference is denominators. So if you divide it by R, if you remember, we actually divided by delta x, but doesn't matter, the distance, it would, so here it would be R squared. So V divided by distance is electric field. So you find electric field by just dividing potential by R. And again, if you want to go from potential energy to force, you again divide by R. As you can see, the only difference is in the denominator. Or if you want to go from potential to potential energy, then the only difference is, of course, the charge. So multiply this by Q2, both sides, and the left-hand side and the right-hand side, they give you, so if you look at this equation that we learned, it gives you the potential energy. So, and you have to notice that these two formulas, they are valid in all cases, such as you can have parallel plates connected to a battery, or you can have point particles like these. So these are point particle formulas, or let's put it this way. So these, all the formulas that you see in the table, they are valid for point particles, point charges, but you can also have parallel plates and they can be connected to a battery. So in these cases, we can't really use the formulas for point particles, but these two formulas, they are still valid also for cases where you don't have point particles, but instead you have the battery and the parallel plates. So in this example, what we have is we have two charges, plus Q and negative 2Q, and the value of Q is given here. So one of them is placed at the origin. The other one is that's placed at 1 meters. So this is 1 meter. The first part of the question is find the electric potential at x equals 0.5 meters. So how do you find electric potential or potential? They're the same thing. So how do you find potential at this point? And this point is 0.5 as given in the problem. So this charge will create potential at this point. How do you find it? Well, K, Q divided by the distance, 0.5. Remember, this is, we don't take the square. It's just R for the potential. And this charge will also create potential at this point. And again, the distance is 0.5. So this distance is also 0.5, or we can write it as 1 minus 0.5, same thing. And notice that the second charge is negative. Now, if you plug in the Coulomb's constant, and also for Q, plug in this number, you will find the potential at x equals 0.5 is negative 73.9 newtons meter per coulomb, or shortly just volts. So in the second part of the problem, we have in part B, the electric potential, or just potential, vanishes at some point between the charges, that is, for a value of x between 0 and 1. So in this case, x is not 0.5, but it's somewhere in between 0 and 1. So if the whole thing is 1, then if I call this distance x, then this part becomes 1 minus x. And in part B, it's a different question. So it says at this point, potential is 0. Now it says find x. So at which point in between these charges, the potential becomes 0. So we will equate potential to be 0. And the potential, of course, it has contributions from both charges. The contribution from the plus charge is kq divided by x. This distance is x. And from the negative charge, it's k, negative 2q, it's the charge. And now this distance from this negative charge to this point is 1 minus x. Now, what we have to do is just solve this equation. We know k is this value, and q is this value. So plug in the numbers and solve for x. Turns out 0.333 meters. So if this point is if x is 0.333 meters, if you calculate the potential at this point, turns out it's 0. Now let's also talk about this graph here. The potential that's created by plus charge, it goes to infinity right exactly on the charge. Because when you think about this formula, at a 0 distance from the charge, when r is 0, of course you can't plug in here 0, but imagine that you take the limit where r goes to 0. So right exactly on top of this charge, the potential diverges, it goes to infinity. So that's why it's plotted like this. But as you go away from the charge, to the left or to the right, the potential goes down as 1 over r. But the point here is the potential values, they are positive values created by positive charge. If you have negative charge, then you will have a negative sign here. So any potential created by negative charge will be at negative values. So potential at these points, they are negative values. Again, it diverges, it goes to infinity, but negative infinity, right on top of this charge. And now, so this plus charge produces positive potential values, and the other one, negative charge, produces negative values. And there's a point where the potential created by the plus charge and the minus charge, they cancel each other completely, and at that point the potential becomes 0, and the location of that point is x equals 0.333 meters. Okay, how does the total potential created by two plus charges look like? In here we had one plus and one minus, but what happens if we have two plus charges like this? Well, on top of them, it would diverge to plus infinity because of this divergent behavior. When you take the limit going to 0, it will go to infinity, but plus infinity. So that's why they're drawn like this. Of course, if you go away from it at a distance to the left or to the right, it will be a positive number, a finite number. And in this case, in between, you are always summing up or adding up positive values. For example, at this point, at this point, at this point, there's a contribution, positive contribution to potential from this charge and also this charge at all points in between. So when you add positive numbers, you never get 0 or negative, you always get positive numbers. And you can see that in between, the potential never goes to 0, it's some positive value or positive values. In this case, at one point, it went to 0 because the potential from this one plus the potential from this one minus, they canceled at this point. So the potential was 0. Okay, now let's have not two charges, but three charges. So here, find the total potential energy of the charge plus 3q. So we have this charge, find its total potential energy. Well, this charge, we have to think, so it's interacting with this plus q charge and also interacting with this plus 2q charge. So we have to think about this pair and then this pair and calculate potential energy for each one. Let's call U1, U2, and then sum them up. So for this one, it's going to be Q3Q divided by the distance, square root 2 times D. If you have a triangle like this, D, and this becomes square root 2D. And for this pair, it's going to be 2Q here and 3Q, again divided by square root 2D. And if you sum these up, you end up with 9k q squared divided by square root 2d. So this is the first way to solve this problem. We basically use the equation, the formula k q1 q2 divided by r. Now there's a second way. Let's take a look at it. Now in the second way, first calculate the potential V. Now we will do it with potential at position of 3q, where the 3q is. So these two charges, they would create potential V, the total potential V at this point. Let's calculate it. And then when we calculate it, so once you know the potential coming from Q and this 2Q, now I can multiply this potential by the charge by using this equation. So U equals Q times V, and it would give me the energy of this plus 3Q charge. So first we find the potential. So this plus Q creates potential energy at a distance square root 2d distance at this point, this much. And the second one creates again potential this much. So it's K Q. So we are using the formula V equals Q K, sorry, K Q divided by R. Notice that there is no, we don't mention this 3Q, because when you calculate potential, you have only one Q. So this charge, so we are interested, so when you calculate potential at this point, you are not interested in 3Q. You're just interested in calculating the potential from plus Q and plus 2Q at this point. And that potential is this. So now we know V at this point, which is this value. Now, once you know V, multiply V by the charge that you place at that point, which is plus 3Q. So if you do the multiplication, then you find 9kq squared, so that's the potential energy, divided by square root 2d. And if you compare it with what we found in the previous slide, you will see that's exactly the same expression. So these are the two ways that you can solve these types of questions. So here's another question. 4-point charges are arranged at the corners of a square here. Find the electric field E and the potential V at point P. Now, potential is a scalar, so it doesn't have any direction. It can be only positive or negative. This is important. But E, electric field, is a vector, so we have to be careful. Now, potential from each one, so we will use this formula, K, Q divided by R. So this one creates a potential at P. This one also creates. So all of them creates potential, and it's a scalar value. So, and because that's a scalar value, we can basically add them up. So we don't have to do vector addition. So let's look at the solution. So the potential at point P from each one, the total. So this one creates potential, negative KQ divided by R. This is also a negative charge, and it creates negative potential. So I'm taking this distance to be R, and because P is the middle point, so it's always R, the distance is R. So these two plus charges, they will create positive potentials. And if you add them up, they add up to 0. So the potential at the middle point is 0. Notice that we are doing just algebraic addition because potential is a scalar. This is important. Now, as for the electric field, it's a vector. So we have to be careful. So we have to do vector addition. Now, let's look at the electric fields that each of these point charges create at point P. So first of all, this is a negative charge. So the electric field that it creates at point P in the middle point will be towards itself, because remember, if you have a negative charge, the electric field lines are towards that charge. So in this case, it will have this electric field. And this charge, remember, if positive charges, they have electric field lines going out from them. So at this point, it will create this electric field. So this charge will create this electric field, and this charge will create this electric field. Now, if you add these two vectors, so they will maybe add up to this vector, and these two maybe will add up to this vector. And if you add these two as well, then the total electric field will be in this direction, something like this. So the electric field is not zero, but the potential is zero at point P. So let's move to now equipotential surfaces and the electric fields. So contour maps have closed curves. You can see that they're all closed curves. So each curve and correspond to the same elevation. So for example, here, if you're at the summit, the elevation is 450. And if you move out from the summit, let's say if you go down, the elevation goes down. But for a given curve, let's say this curve, let's choose this curve. If you're on this curve, all points on this curve has the same elevation, which is 350. So each curve correspond to a points on each curve correspond to the same elevation. And the denser or the closer the curves, the steeper the slope. Now look at the curves here, they're denser. And here, so because they're denser, this part is steeper, as you can see that. This part of the mountain or the hill, it's steeper if you compare it with this part. And this part is less steep. This part is less steep. And if it's less steep, you can see that the curves are, or the contours are less dense. Now, can we show electric potential V the same way? And the answer is yes. So here, denser circles, we will have circles. They would correspond to higher potential change. So for example, in this figure, we have two-dimensional space here. We have a positive charge in the middle. So that positive charge creates potential and also electric field around. As you can see, electric fields go out radially. And if you're interested in the equipotential curves, in this case, they will be these green curves. So on each green curve, all points on a given green curve, they correspond to the same potential. For example, the largest green curve circle, the outmost circle, it's at 1 volt. Here, 1 volt. So this circle, any point on this circle, it has 1 volt. Its potential is 1 volt. The second largest circle is at 1.5 volts. Here, it's this circle. Any point on this circle is 1.5 volts. And the third largest circle is at 2 volts. And this one is at 2 volts. As you get closer and closer to the charge, you can see that the voltage, the potential increases. And we already know why that happens. So remember this formula, Q divided by R. So here Q is this positive charge. As you get closer and closer, so you get smaller and smaller R values. If R gets smaller, and because it's in the denominator, so we have larger and larger potential values. And in fact, we learned that right at the top of that charge, the potential actually diverges to infinity. In this case, we have plus charge, so it will diverge to plus infinity. Now the question is, what are the average electric fields at the regions shown by, in this case, red braces? So red braces. So we have a red brace here and another here. So what is the average electric field here in this region? So between the greatest circle and the second largest circle, so in this region. And also, what is the electric field here? Let's start with this one. Electric field in this region, we will use this formula that we learned previously. So if you have potential difference, in this case, this circle is at 1.5 volts. This circle is at 2 volts. So the difference is 0.5 volts. And the distance here is 1 meter. You can see it maybe here. It's not given in the figure, but you can take it as 1 meter. So if you calculate it, it's 0.5 volts per meter. And remember, volts per meter is one of the units of electric field. The other one was newtons per coulomb, which is the same thing. Okay, so now we are going out, so we will go away from the charge. Now we are here. Now we will calculate electric field in this region. So now the voltage difference between these 2 points. So this was at 1 volts. This curve, this equipotential curve, was at 1.5 volts. Again, the difference is 0.5 volts. But now the distance is 4. So between this point and this point is like -6. So the difference is 4 meters. And you find the electric field to be 0.125 volts per meter. So it's less, as if you compare with this one. As you go out, the electric field gets smaller. And you can even tell it from the figure. Remember, the electric field lines, when they are dense, then that means electric field is stronger here. When they are less dense, as you can see here, the purple vectors, they are less dense. As you go out, you get far away from the charge, they get less dense. That means electric field strength goes down. So the observation that we can make here, the electric fields are decreasing radially, so their magnitude is decreasing, which is what we would expect, because for a point particle, the electric field strength is given by this formula. And you can see we have r squared in the denominator. As you go out far away from the charge, it makes sense that the electric field lines go down. But in this slide, what we learned is that we can either use this formula, or we can also use the potential and the distance to find electric fields. Now, equipotential surfaces, remember, equipotential means a surface or a curve where if you are on it, the potential at all points on that given circle or surface is the same. So here you see equipotential surfaces or curves for two charges. In this case, we have plus plus, and on the right-hand side, we have plus minus. Potential is the same on a given curve. Let's say you choose this curve, so all points have the same potential on that curve. The value of the potential is the same. If you move to the outer curve, now the potential goes down, but all points now on this curve, they have the same potential. Let me go back to this figure here. Of course, if you change the curves, the potential changes. In this case, the height changes, which is related to potential. Remember, for gravitation, for gravity, it was g times h. So g is some constant, so potential depends on h, the height. But for any chosen curve, let's choose this curve. So at all points on it, the elevation or h or the potential is the same. So it's the same value, which is 300 for this curve. So let's go forward. The other thing is the potential can be, which is kq divided by r for point charges. It can be positive or negative depending on the sign of the charge. So if you have two plus charges, of course, the values are always positive. If you have one plus, one negative, so the plus charge produces positive potential, negative charge produces negative potential. As you can see, these values are for the negative potential. The other observation we can make is that electric fields go from high potential to low potential. You can see, for example, from here, they go from the purple ones, from positive charge, high potential, to low potential. You can also see here, this part is high potential. The place where the negative charge is at is low potential. So the electric fields go from high to low. Even these ones, they actually curl like this and then go in to the low potential. And in this case, of course, these are plus plus charges, so we cannot connect these. But electric field lines again go from high potential, so this point is like the hill, the top of the hill, and these are like lower elevations you can think of, even lower heights. So they go from high potential to lower potentials. The other thing that you can see from these figures, the equipotential surfaces, so these are the same V surfaces or curves, and the electric field lines, they are perpendicular to each other. So you can also look at here, the equipotential surfaces and the electric field lines, or the electric fields, they are the curves and the electric fields, they are perpendicular to each other. And also plus charge particles go from higher potential to lower potential. Higher potential could be, for example, 40 volts. Lower potential here could be 20 volts. So they go from high potential to low potential, plus charge particles. So that what it means is if I place a plus charge here, it will go from high potential to low potential. For negative charges, it's the opposite. So if you place a negative charge here, it will go to high potential. So from low to high for a negative charge particle. Okay, so potential V is the same on the surface of an ideal or perfect conductor. So it could be a metal or any other conductor. So potential at all points are same on the surface. So same here. If potential at this point is V, 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 the same potential. Now imagine that if the potential weren't the same everywhere on the surface, let's say you have 40 volts here and you have 20 volts here. What would happen? Well, we just learned in the previous slide, the charges would flow from high potential to low potential, right? So an electric current would happen by itself. An electric current would flow until the charges are redistributed, and the potential until the potential is the same everywhere on the surface. So even if you have potential difference, the charges will move, they will redistribute, and in the final equilibrium case, again, the potential at all points on the surface will be the same. But what about electric fields? At the sharper parts of the conductor, charge is more concentrated. You can see that there's more charge at the sharp edge or the sharp part than this less sharp part, so less charge here. And the electric field is stronger at the sharp points. You can see that the electric field lines, they are denser than here. So to summarize, at the sharp points you have more charge, stronger electric field. Here you have weaker electric field, less charge, but the potential is the same. The potential is the same at all points. Why? If the potential is not the same, then you would get a current, the charges would flow, redistribute, and until when the potential at all points on the surface is at the same potential. So this is a voltmeter here in this picture. So voltmeter with its it always has two probes, and it measures. So the probes measure the potential difference, delta V, on the surface of an ideal conductor. There's no potential difference, even if there's charge, extra charge. If you measure the surface, you will find no potential difference. And we just talked about it in the previous slide. The potential at each point on the surface is the same. Remember, voltmeter change, it measures potential difference. So V1 minus V2. But if these both are V, then you get 0. So even if it's charged, if you measure the same conductor at different points, because the potential is at the same at all points, and because the voltmeter is measuring potential difference, it will measure 0 if it's a conductor. That's important. If we are talking about an ideal conductor, which also means we can also say perfect conductor. So voltmeters probes touching the same conductor would measure 0 volts. If you have the voltmeter one end, one probe, touching this conductor, charge conductor, and one probe, the other probe, touching, let's say, to the earth, then there would be some potential difference because earth is not charged. This conductor is charged, then it would measure some potential difference in that case. So with the voltmeter, you always measure the potential difference between 2 points, never potential itself at 1 point. So we don't really measure potential at 1 point because this voltmeter, they always have 2 probes. You always measure the potential difference between the probes. Now, if we come to human body, now you know that human body conducts electricity, and that's why we actually get electric shock when we touch high voltage. So the human body is a conductor, but it's not a perfect conductor. So remember, at perfect conductor, at every point you have the same potential, But if you have an imperfect conductor like the human body, the potential at different points will be different then. So you will have different potentials. So there are potential differences between different parts of the body. And indeed, if you measure the potentials at different points on the body, you will get a signal. So you will get a non-zero signal. For example, a human heart, it has its own natural pacemaker that creates potential differences of millivolts. So when the heart is working, it creates potential differences on the order of millivolts. Remember, a typical battery is 1.5 volts. So it's about 1,000 times smaller than the battery. So the muscles contract to pump blood. So that activity creates potential differences. So the potential differences created are by the heart, they are measured by electrocardiography. So it's called ECG or EKG. Again, the reason why we have different potentials on human body or human skin is even though the human skin is a conductor, it's not a perfect conductor. So the same potential only happens on the surface of a perfect conductor. When you have imperfect conductor but still not perfect, then you would have some differences in potential, and indeed you can measure it. Let's move to capacitors and dielectrics. Capacitors are these elements, circuit elements that you may have seen on electric circuits. So capacitors are used to store charge like batteries. So basically use them to store charge. But there's a difference. Batteries work chemically, but capacitors are simply two conductor parallel plates. So just like these two parallel plates, there's no contact between them. They're not connected with a wire. So they're at a distance. And indeed, you see a capacitor here. The inside is basically there are two conductors and they're separated. So they don't really touch each other. There's a separated material in between and they are wrapped in a cylinder. So we have this cylinder shaped, but again, it actually has two conducting sheets, which are separated by non-conducting material so that they don't touch each other. So different capacitors can store different amount of charge. The charge storing capacity of a capacitor is called capacitance, and it's shown by C. The amount of charge Q that can be stored for a given voltage difference, V, is Q equals capacitance. That's a property of the capacitor. These capacitors, they all have different capacitances. So you connected the battery, and so if you multiply the voltage of the battery with the capacitance, you can find the charge collected on that battery. So that charge is the charge, not both. So it's basically the charge on each plate. So Q equals CV. That means if you apply more voltage, if V is more, then it will store more charge. So in the case of charging, you connect the battery terminals. Again, there is no connection between the plates. Otherwise, the charge, if you connect these plates, there will be current, so the charges will flow. So that wouldn't be a charging. So for charging, they should not touch each other, only they're connected to the battery. So when these plates charged, which means you have positive charges on this plate and negative charges on the other conducting plate. So once they are charged, you can measure the voltage between them. So now remove the battery, and if you measure the voltage between them with the voltmeter, because we charged it with 12 volts battery, now you will measure the voltage difference to be 12 volts. Okay, here's an exercise. We have a capacitor of 0.55 microfarad. So farad is the unit of capacitance, and micro is 10 to the negative 6. So it's charged to a voltage 12 volts. So we connected to our capacitor a battery, which is 12 volts. What is the magnitude of the charge on each plate of the capacitors? Remember, so in this case, let's say plus and minus. So we have plus Q here, negative Q here collected. So how do you find it? Um, so what is the magnitude of the charge on each plate of the capacitor? So we are going to use Q equals CV. Now C is the capacitance is 0.55, micro is 10 to the negative 6 farad, and we charged it with battery of 12 volts. And you multiply these numbers, and you find the charge on each plate to be 6.6 microcoulomb. So on the positive, we have this much, and on the negative, we have also this much charge. So this amount is Q. So what's shown here? So not 2Q, so this is Q. So that means we have 6.6, negative 6.6 microcoulomb on this plate. And on this plate, we have positive 6.6 microcoulomb as well. Now in part B, what is the capacitance of the capacitor that has a charge? So here now Q is given and the voltage is given. Now again, we use the same formula, except now we have to solve for the capacitance. So it'll be Q divided by V. So plug in the numbers. Q is given in this part B. The voltage is 9 volts. Do the division, and you will find the capacitance in this case is 0.21 microfarad. So the unit of capacitance is farad. So assume capacitor plates as infinitely large charged sheets. So each charged plate produces its own electric field with strength. This goes back to chapter 19. So sigma divided by 2 epsilon 0. Here sigma is the charge density, so it's the charge per area. Epsilon 0 is the permittivity of the space. It's just a constant. So the reason that we are using the infinitely large charge sheet approximation, even though these are not obviously infinitely large, this electric field, this is a good approximation when you have parallel plates. So the electric field between the plates due to plus plate, so this plus plate, it will create electric field here in the down direction. And the amount will be this, sigma divided by 2 epsilon 0. And of course, sigma is by definition Q divided by A. Now the electric field, the negatively charged plate will again in the middle region will create electric fields towards itself because it's negatively charged. So it will be again down in the downward direction. and the amount will be again the same, the magnitude will be the same. Now the total electric field between the plates will be the addition of these two. And now we have Q divided by A divided by 2 epsilon 0, so they're the same, so just multiply by 2, then we get this Q divided by A epsilon 0. So this is the electric field strength in the middle region. Now we learned another formula. It was in this form: E equals the change in potential divided by change in distance. We can rearrange it to write it as V equals E times D. So in other words, if you know the electric field here in this region, and if you know the distance D, then you can multiply these two and it will give you the potential difference in between. So we can write it as potential difference as well. Okay, so now here we calculated the electric field to be Q divided by A epsilon 0, and the distance between the plates is D. Now if you combine this with Q equals CV, which is something that we just learned, now we can get a formula for capacitance from here. So V here is Q divided by C. So instead of V here, we will write Q divided by C. And on the right hand side, we have Q. So we have Q divided by A epsilon 0 times D. So these Q's cancel each other. So C becomes A times epsilon 0 divided by D. And again, so here's the unit of capacitance is farad. And capacitance is again, it quantifies the amount of charge that a capacitor can hold. Now, epsilon 0 is the permittivity of space. It's a constant number. Now, there's A in the numerator. So A is the area here, area of these plates. Of course, these plates are two-dimensional like this. So A is the area. So if area is large, if you increase the area, then the capacitance increases, and that makes sense because if you have more area, then you can store more charges. That's why larger capacitors, if you have a larger capacitor, then it can store more charge. Now, if you look at the denominator, there's D. So if you increase D, which is the separation between the plates, if you increase, so if you make the plates like this, more separated like this, then the capacitance, so if you increase D, the capacitance goes down. So by increasing D, you make the charges far away, so their interaction strength or the force between them, it goes down, or the electric field goes down. So because of that, you can store less charge. So increasing D decreases capacitance. Now let's move to dielectric materials. Dielectric is an insulator. Insulator means it does not have free electrons. Remember from chapter 19. So in a dielectric material, in an insulator, the electrons are tied to their atoms. Electrons cannot move through the material in the insulators. In metals, conductors, they can move, but in insulators, they cannot move. But the only thing they can do is to get polarized. If there's electric field or charge you can think of in either terms, the atoms, they would get polarized. So normally you have the atom, let's say, and the electrons around. And if you have a charge close by, if you bring a charge or if you bring electric field, what would happen is these electrons would move towards the positive charge. So the atom would become more like this. So positive charge from the nucleus on this side and negative charge from the nucleus on the left, from the electrons on the left side. Remember, this was polarization. Okay, so a dielectric is an insulator when placed between the plates of a capacitor. So anything that's placed between the plates of the capacitor, any insulator, we call it dielectric. And this increases the capacitance. So it's a good thing if you want to increase the capacitance. Remember, you could either increase the area or you have to make D smaller. But there's another way. You can place in between a dielectric material. So this increases the capacitance C, which means the plates can store more charge for a given voltage. So let's say voltage is fixed, let's say 9 volts. If you want to store more energy, if you want the capacitor to store more energy, the only thing that you can do is to increase capacitance. And one way to do that is to place a dielectric material in between. Each material has its own dielectric constant. So if you don't put in anything, it means vacuum. And anything that you put in, any material, paper, Teflon, rubber, water, it actually increases. So it has some kappa, which is the dielectric constant. That dielectric constant is larger than, the value is larger than that of the vacuum. So vacuum means nothing inside. So for any K, so let's say C0 is for the case, the capacitance for the case where there's nothing in between the plates, no material. And if you place one of these materials, now the capacitance of this capacitor, it becomes C0 times kappa, and kappa is, as you can see, is a number that's greater than 1. So any dielectric material that you put in, it will increase the capacitance. Okay, in this example, we have, so it says a parallel plate capacitor is constructed with plates of area, so A is given, and separation, which is D here, D is given. The space between the plates is filled with a dielectric with dielectric constant kappa. When the capacitor is connected to 12 volts battery, each of the plates has a charge of max. So this is the Q. What is the value of the dielectric constant K? First, we use this formula, Q equals CV. Now from here, we find the capacitance. So now remember, there are two formulas for capacitance. One of them is this one, which relates the capacitance, Q, and the voltage. The other one is, again, capacitance formula, but it relates the capacitance to the properties of the capacitance. For example, kappa, the dielectric constant of the material that's put in between the plates, the area of the plates, and the distance between the plates. So now we move to this one. So in the second one, now from the first one, from the first line, we calculated capacitance. So we know C. Epsilon 0 is just a constant of nature. A is given here. And you have to use them in SI units. So this is already meters squared, but for D, you have to convert this to meters. So D is given. So everything is given except kappa. And indeed, the question is about kappa. So if you plug in the numbers and solve for kappa, you will find it to be 6.7. If the electric field in a dielectric becomes too large, so you can have dielectric materials, paper, mica, Teflon, and rubber, or any other material, even air, it's different than vacuum. Air, it also has a dielectric value. So if the electric field in the dielectric becomes too large, so let's say you have capacitor plates and you placed some dielectric material here, and if this voltage that you apply, if it becomes too large, it can break neutral atoms into ions and electrons within the dielectric. So it can break the electrons from the atoms, thereby enabling the material to conduct. So even though this is insulator, normally insulator, if we apply a huge amount of electric field, that electric field may be able to break the atoms and the electrons. So it may pull the electrons from the atoms. Then the material, now if the electrons can move freely, then the material will be a conductor. And this is called dielectric breakdown. And the electric field strength at which this happens is called the dielectric strength. This also determines at what voltage the capacitor breaks. So when you make experiments at the lab, you have to be careful. So for example, for air, it's a dielectric medium. Air is not a conductor, it's an insulator. So it's a dielectric medium. But if you apply high voltage difference of like 10,000 volts, so it's called, so this here, it's called Jacob's ladder. So there's this source here and it applies 1000 volts. Notice that there's no connection between these two wires. It's just like the capacitor here, capacitor plates. Instead of plates, we have wires, but doesn't matter. So if you apply this much voltage, what happens is it ionizes the air. So now air, it has atoms, right? It has hydrogen gas, it has nitrogen gas, it has CO2, oxygen, so it has several gases. And these atoms or molecules, they have their protons and electrons, but if you apply really high voltage like this, the electrons will be separated from the protons, from the ions. So even though initially we have neutral air molecules, then we will have ions which are positively charged and electrons which are negatively charged. Now, this much electric field may create a plasma. This is called plasma. If you have positive and negative charges free to move, then that's called plasma. So the electrons and atoms become free. This is called plasma. And because this high voltage, you can think of this also creates electric field from high voltage to low voltage. There's electric field, and electric field separates the electrons from the ion cores, which are positive. And when that happens, you see these arcs, electric arcs happen between the terminals. And the light that comes out, it's happening because when you break the electrons from the atoms, or when you put the electrons back to the atoms, you get a light that's emitted. So that's what you're seeing here. And indeed, that's the same mechanism behind behind lightning. And make sure you look up Jacob's ladder on YouTube, and it's really interesting setup. Okay, let's move to the last section, which is electrical energy storage. Storing positive and negative charges on opposite plates requires energy, and that energy is coming from battery. The energy stored in a capacitor is given by Q squared divided by 2C. C is the capacitance. Now you can use Q equals CV that we learned in the previous slides. For example, if you, instead of Q, if you substitute CV, so this will be CV squared divided by 2C, which will give you this, CV squared divided by 2. Or if you get rid of C here by again using this formula, you can rewrite U, the potential energy, as QV divided by 2. So you can use any of these. They are equivalent. We can also write this in terms of electric field between the plates. Remember, when you have plates, when there's a potential difference, whenever there's potential difference, and whenever there's distance, then there's electric fields. In this case, plus, minus, so electric fields will be in this direction. So this is plus charged, this is negatively charged. So we can write energy in terms of also electric field. So we will use this formula for capacitance, and also V equals E times D, or if you remember, this was also like this. Whenever there's potential difference, there's electric field, or delta X or D, doesn't matter. So now we start with 1/2. So instead of C here, we will use this one. And instead of V, we will use ED, electric field times D, but we have to take the square of it. So here. So we can rewrite it as, so we have D squared here, we have D here, so finally we have D, and we have area, we have E squared, electric field squared, and permittivity of space epsilon 0. So if you want to write the energy stored in a capacitor in terms of area, this separation between the plates and also the electric field, then you can also use this formula. So these are all equivalent formulas. Now the last term here, A times D, this is volume, right? If you have two plates that are connected to the battery, so area, and this separation is D. Now A times D, it actually gives you the volume here. Gives you the volume here. So the volume between the plates. So if you remove it, so if you remove this part, or let's do this, if you divide both sides with AD, which is the volume, now this is gone. So this energy, potential energy per volume, let's call it lowercase u, then it's given by 1/2 epsilon 0 electric field squared. So if you want to calculate the energy density but not energy, then you can use this definition. Now, energy stored in a capacitor can be put to a number of uses, for example, keyboard keys, camera flash, touchscreen, etc. In the case of keyboard keys, now there's this, so there are two plates. It's basically a capacitor. When you push the key, what happens is the distance between these plates, which is D, it gets smaller. So remember, capacitance depends on the distance between the plates. So the computer or the electronics of the computer, it constantly measures this capacitance here. And when you push the key, because the capacitance changes and it changes other things in this circuit, so it knows that the key is pushed. So it's basically, it knows it. The computer knows that the circuit, the key is pushed because it monitors the change in capacitance. The capacitors are also used in flashes. So this large piece here is the capacitor. So it takes some charge, sometimes a couple seconds to charge it completely, and then when you take a photo, it flashes. So it discharges in a very short amount by producing really bright image. In the case of touch screens, what you have is you have basically two plates. So there's two materials, two plates on top of each other, which are separated by some insulator. So this blue and the green, the yellow and the blue, they are two different plates. They don't touch each other, so they're like, so it's basically like a capacitor. But when you bring your finger close, your finger changes the capacitance here, because now normally the capacitance is between these two plates, but now when you bring your finger acts as the as the top plate of the capacitor, and the one of the plates here acts as the lower plate. So you, again, when you touch on the touch screen, you basically change the capacitance locally. Again, this computer or a tablet or smartphone, its circuit can know that at which point the capacitance is changed, so that you can use the touch screen. So that's all for this video. See you in the next lecture.